have the same conversation. It's like 20 times a day.
All right, let's do a problem. Get us going here.
It's a great compliment. Yeah, everybody's Starbucks in there. Everything healthy's half off.
Uh-oh. I don't see my mouse. Okay.
It's just not a good day.
It's just not supposed to happen today.
Okay, everyone should go.
All right. Where's one? All right, I'm just going to have to make it up. All right, limit. Let's let x go to infinity of, no, I won't do natural log. I'll do x minus 1 to the 1 over x. All right, so where is this headed?
It's headed to infinity.
The base is headed to infinity, right? Where's the exponent headed? To the 0, right? 1 over infinity is going to go to 0. Is this an indeterminate form? Why? Base is trying to get real big, but anything to the 0 should be 1. So this is a problem. All right, so when we see one of these, we want to bring in the natural log. So how do we do that? Yeah, turn it into an equation first, so you can rewrite it as y equals this limit. Like that. And then you apply the natural log on both sides. And what was it about that natural log in the limit? You could pass the natural log through the limit. So I'm going to do that without actually showing. I'm just going to bring the natural log in here, and then it's just natural log of whatever was there. And the entire purpose of that was to do what? To be able to drop that exponent down, right? So let's drop the exponent. The exponent will come down in front of the natural log. So now I have natural log y equals limit x approaches infinity, and then I have 1 over x times natural log of x minus 1. Now when we do this, we should still have a problem. And we can see what it is, yeah? This is going to go to 0 times, and then natural log of infinity is still infinity, right? The natural log function as you go to infinity goes up, keeps going forever, up. So this is going to be infinite. So we still have a problem, but now we know how to deal with these. We take one of these and we drop it down. So which one would you like to drop? The 1 over x. When we take the derivative, hold on though, let's do that. Well actually, let me see, I'm going to leave the natural log of x minus 1 here. I'm dropping 1 over x down. It's just x. It's just x. Now you can kind of see that right here. Like if I don't even think about dropping, if I just rewrite this, couldn't I just slide that natural log on top of that? And then I would have had a fraction. But if you want to look at it as dropping this down, you have to look at it as 1 over x. That's what we're actually doing, right? And then when you do 1 over a fraction, it flips, and then just this right here just turns into x. So either way you look at it, you should get an x down here, just x. Got it? Now if we check again, x goes to infinity. Natural log of infinity is infinity. X goes to infinity, we get infinity here, so we have infinity over infinity. So we can do L'Hopital. So I'm going to say natural log y equals, by L'Hopital's rule, limit x goes to infinity of what? 1 over x minus 1 over 1. So derivative natural log of something is 1 over it. Derivative what's inside is 1, so I don't need to write that. So that's derivative of the top. Derivative of the bottom is 1. And now let x go to infinity. What do you get? Fixed over infinity goes to 0 over 1? 0. So this is just 0. So is our answer 0? No. We know that the natural log of y equals 0. And then to get y back, we just do the inverse of the natural log, which is e. And e to the 0 is 1. And the left side is y, right? And that's what we are interested in. We had called this limit y, and we're coming up with a conclusion that y is 1. So the answer is 1. Okay? Questions?
Based on the look at so I know why you did the e to the ln y, but do you not do e to the, well, I guess it cancels out, right? For the right side like this.
Well, anything to the 0 is 1. So e is a number, right? So
Yeah, I'm just curious why you didn't do e, ln y on both sides, typically.
no, because this is what I started with, right? The left side has ln y, the right side is 0. I'm doing e, I'm applying the exponential function to both sides of the equation.
Okay.
And again, I'm not really, it's weird when you say this. I'm using the property of the inverse function being a one-to-one function, which was this. It says this: if x equals y, then e to the x equals e to the y. That's actually what I'm using. This was a property of one-to-one functions. That if you have equality, then if you take the left side and the right side and you plug those values into the function, whatever the function is, x goes into the e function, y goes into the e function, you'll maintain equality. So I'm not really multiplying both sides by e, or like not even taking e of both sides. I'm just using the property of e being a one-to-one function. But we could get bogged down with that, so that's why I say we're applying e to both sides. Okay, good. Let's try this one. I'm making this one up. I have no idea what's going to happen here. All right? It just seems interesting to me. Do we have an indeterminate form? Where's the base headed? Sine of 0 is 0, isn't it? So this is, the base is 0, but the exponent is also 0, and is that a problem?
Yes.
Yes, the base wants to be 0, but anything raised to the 0 wants to be 1. So that is an issue. But same exact process, right? We're going to go ahead and try and get that sine x to pop out, but we have to bring the natural log in on both sides to do that. So I'll call this thing y. I'll do natural log on both sides. I will pass the natural log through the limit. And then I'm allowed to pop that sine x out. I'm a little concerned right now. I don't know, maybe it won't be so bad. that should be 0 times infinity. Because sine of 0 is 0, but natural log of 0 is undefined, but it's a limit, so we're approaching 0, right? This right here is approaching negative infinity, and this is approaching 0. Do y'all follow that? Natural log of 0 is undefined. But as we've seen, as you approach 0 from the right, it's dropping down. So we still have an issue. Look, if you ever have an indeterminate form and you bring the natural log in on both sides and drop this exponent out, it's never going to fix the problem right there. It's always going to still have a problem, right? You're going to have to use L'Hopital's rule to get this. All right, are we ready? What are we going to do? Drop one of them. Drop the sign? I think I'll drop the sign. I like that idea. Natural log y equals, I'm leaving natural log of sine x on top, and on the bottom I'm putting, oh, I forgot the limit. Limit x goes to 0 from the right. I have natural log sine x over what? What is it? It would be 1 over sine, wouldn't it? 1 over sine on the bottom? Cosecant. 1 over sine is cosecant, right? So that's the same thing. Feel good? And now I'm going to just trust that I still have an indeterminate form. I should. You could check it. This goes to negative infinity, and if you look at cosecant function, oh shit, I may as well do it. All right, so here's sine, right? To draw cosecant, what we do is we draw vertical asymptotes at all the x-intercepts of sine, and then we draw these little, like, almost like parabola-looking things. That purple is cosecant. That's from pre-cal. And as I approach 0 from the left, from the right, goes to infinity. So I do have infinity over infinity. Negative infinity over infinity, but who cares? It's still an indeterminate form. So I can use L'Hopital. All right, derivative of the top. 1 over sine x times cosine x. Chain rule, right? Derivative of natural log of something is 1 over it times derivative of what's inside, which is cosine. I'm really not happy about this, but let's see what happens. What's the derivative of cosecant x? Minus cosecant x cotangent x. Whew. Oh, wait a minute. Hey, that's not so bad.
Is that tangent, right? Or cotangent all the time?
This right here, cosine over sine, is cotangent x, isn't it? Which cancels with this cotangent x. So I just have 1 over negative cosecant x, which is really what? What's negative 1 over cosecant x? The negative down here can be on top or bottom, right? Doesn't matter. 1 over cosecant is sine, isn't it? So this is really just natural log y equals limit as x goes to 0 from the right of negative sine of x. And sine of 0 is 0. This just goes to 0. Natural log y equals 0. Do e on both sides. Y equals 1 again. Are there any questions? Because I went through this last little part kind of quick. Any questions on this last couple of cancellations and things?
So 1 over the cosecant x, that's negative sign? Or how'd you get that?
The negative was already here.
Okay, so it's just sign.
Yeah. So if I just said what's 1 over cosecant, you would say sine. But the fact that we had the negative there made it negative sine. Yeah?
So you didn't have to take the derivative of that?
No, because this isn't a problem. If I let x go to 0.
It's a problem.
What's that?
You only do it if it's a problem.
Yes, if we have 0 over 0 or infinity over infinity. All right, so that didn't work out as bad as I thought it was going to be. Yeah, it worked out pretty nice. I'm not going to do it, but this is my next, like, I'm curious what would happen. Like if I replace that with tangent. Because if I let x go to 0, I still get 0 here. And then I would have the same sort of problem, right? Nah, we won't do it. Okay, I think that that's sufficient for L'Hopital. We can put L'Hopital behind us except for the take-home. Have that ready for me next class. And we're ready to move into chapter 4, all right? And I don't have my mouse, so I don't know how I'm going to do this. Did I, like, put it somewhere? Yeah, that's an expensive mouse. Hold on a second. I probably left it in here, but usually people find it and just like put it over here somewhere. I'm gonna check. I'm gonna check right here. Oh, there it is. Someone was nice. All right. Well, chapter 4. Get up here. I'm going to talk briefly before we begin about each of these sections. This is pretty much going to wrap up the course for us, all right? Chapter 4. We might dabble into chapter 5 a little bit, but this is it. This is the last part of Cal 1, all right? Sounds like, okay, we're almost there, but this is a lot of information here, all right? Okay, so let me explain what each of these things are just briefly, and then we'll get into the first section. So these are all applications of differentiation. So how we can apply the derivative to do certain things. And the main goal here, all right, the main goal is that if somebody gives you a function, that you can find the highest and lowest values on that function. So if I graph something, like let's say I have some graph, our main goal is to be able to identify those points, which would be the little peaks and valleys of the function. That's one of the main goals here. And to do this, we're actually going to look at it as two different scenarios. The first scenario we're going to have is where our function is actually restricted to a closed interval. In other words, our function is not allowed to keep going in both directions forever. We're going to stop the function. It's going to have a starting point and an ending point. And we're going to ask ourselves, can we find those peaks and valleys, highest and lowest points, if the function is closed off? Understand? That's what 4.1 is going to be. Finding the maximum and minimum values on a closed interval is what we'll do. Then we talk about the mean value theorem. So let me tell you about the mean value theorem. This section right here, I could move it to the bottom and I could still move through everything else in the section without 4.2 and we would be fine. So it's kind of its own idea. They just throw it in there. I don't know why they do it there, but they do. And so when we do this 4.2, which will be next class, well, maybe the one after that, then keep in mind that after we're done with that, you don't really need it for the rest of the chapter, right? So that's kind of a standalone section. And what that section has to do with is actually a very, very interesting theorem, and it's used a lot. And it's this basic idea. If you have, again, a function that does something, all right? And let's say that this is a continuous function, which means what? I can draw without picking up my pencil. That's the very loose definition of continuity. Okay, so if you start at a point, you draw a function without picking up your pencil, then if I construct a line connecting these 2 points, a line, that line has a slope, right? And that slope, m, I could call it m subscript sec, meaning secant line. The line connecting 2 points on a graph is called a secant line. And the m there would be the slope of that line. The mean value theorem says that somewhere between here and here, somewhere between here and here, there is a point on this curve that if I go to that point, what's the same? Exactly. The tangent line here, the slope of the tangent line, that's not a, well, that doesn't look that great. The slope of the tangent line, right? The slope of this tangent line at that point is equal to the slope of the secant line connecting the 2 endpoints. They're parallel. Do you see that? And that's guaranteed. You will always be able to find somewhere inside the curve somewhere that line, that tangent line, will be parallel to this one. It's guaranteed. That theorem says we have to have that happen. It could actually happen more than once, but it's guaranteed to happen at least once. And the way you can extend that to something that makes a little more sense is let's say you drive to Austin, okay? Let's say you drive to Austin or somewhere north of Austin. Let's say you're going to drive 90 miles. And let's say you make it there in 2 hours. What was your average speed? 45 miles an hour. Your average speed was 45 miles per hour. So you could look at this as being your trip, okay? Time, distance. Then your starting point, 0 miles, 0 time. Your ending point is 90 miles away, and it took you 2 hours. The slope of the line connecting those 2 points is your average speed. So what does this theorem tell us? Seeing if you can make the connection here. If your average speed, if you drove to Austin, it took you 2 miles or wherever it is, 2 hours, you know your average speed is 45 miles per hour, but what does this mean value theorem tell you?
It tells you what your speed was at the average slope.
Okay, close.
Average slope. The mean slope. We talked about it before.
Yeah. I'm trying to see if you can connect it to the picture I have here. This slope right here is your average rate of change, right? From the beginning of the trip to the end of the trip. That corresponds to 45 miles per hour. I just said that what? These will be parallel. Where though? Where will these two be parallel? What's that? No, it wasn't the peak. It didn't have to be the peak.
Is it at the time you were driving 45 miles an hour?
Yeah, there's some point in here where somewhere on this curve I'm guaranteed to get a parallel, right? These two will be somewhere on that curve. My tangent will be parallel to this, which means somewhere while you're driving, what? You had to go 45 miles an hour. It's impossible to have an average speed of 45 miles per hour without ever going 45 miles per hour. You have to achieve your average at some point. Does that make sense?
Yeah.
It has to happen. It would be impossible to not, unless you could somehow teleport yourself across time and space. You can't, but that's why we need continuity. You have to have the continuous function for this to work. So that they call it the mean value theorem. The word mean meaning average. Have you heard that before in statistics? We use the word mean for average. So this theorem for 4.2 is the average value function. On a continuous function, you must achieve the average value at some point in the function, or the tangent line. Okay. Then, like I said, that section's gone and you don't have to worry about it again. And we move to 4.3. 4.3, 4.4 are kind of clumped together. And what 4.3 and 4.4 let us do, derivatives and shapes of graphs, curve sketching. What that allows us to do is take a function, and this time we do not have to cut it off. We don't have to have closed endpoints. And we go and we say, well, can we find the highest and lowest points on this graph? Can we find these? And what's going to turn out happening is that to find those, we're just going to take this problem and even look at it in a bigger picture. Can we just graph it? Just like we did in college algebra. You take a function, you learn how to graph it, right? Quadratics, you learn how to graph those. Polynomials, you learn how to graph those. Rational functions, you learn how to graph those. Now we're just going to say, hey, you know what? Hand me any function. And I'm going to use calculus to graph it. It's the ultimate graphing tool other than your calculator, all right? And this is what they used before the calculators. They used calculus to graph. But in that process of learning how to graph a function using calculus, we will be able to determine these points. This will be kind of just a subtopic within the bigger topic of graphing. Understand? And then, after those two sections, we move into this section on optimization. So there are two sections in this book that cause most students the most trouble, and it is related rates, which were the word problems that you remember those? A spherical ball is growing, blah, blah, blah. How fast is this changing if this is changing? All that, right? Optimization problems are word problems again. But it's all gonna start with the word problem. We're gonna convert the word problem to a function. And then once we've converted the word problem to a function, since we know how to find the max and min values, and we know how to sketch it, which allows us to find max and min values, we can actually optimize our solutions. And I'll just pop this open to see if I can show us a specific example. Let's say that I want to build a can. And I want this can to hold beer. Okay. You want it to hold beer. 12 ounces of beer. All right? There are many different ways that I can construct a 12-ounce can. Right? I'm the company. Right? I can construct that can however I want. I could do that. I could make a very, very short, right? A very, very short can. Understand? Or I could make a can that's like this, right? Michelob? I don't know. I know. Okay, so there's all these different variations of cans. The shorter it gets, the wider it gets, right? Because it has to hold 12 ounces. And the more narrow it gets, the taller it gets. Now, if I'm the company that's building these cans, right, that I'm going to manufacture these cans, every one of these has to hold 12 ounces. I actually have to go purchase the aluminum so I can make my cans, right? And aluminum's not cheap. So I want to make these cans in a way that it requires the least amount of aluminum. So my first question to you is, here's 3 different cans. Let's say they all hold 12 ounces. Do they all have the same surface area? What do you think? If they all hold 12 ounces, will these 3 have the same surface area? Well, we could argue about it, but they don't. Okay? They don't. And we can show it. It's pretty easy to calculate it. But these 3 geometric figures do not have the same surface area. So as a manufacturer, what I want to do is I want to find the dimensions of the can that's going to give me the smallest surface area but still hold the 12 ounces. Because that would then cost me the least, wouldn't it? So what I could do, let me see if I have it here. What I could do is I could come up with a function that the y-axis is the surface area of the can and the x-axis is the radius of the can. So somehow, as I adjust the radius, right? As I adjust the radius, big radius, small height, medium radius, medium height, small radius, big height, right? I could somehow connect the radius of these 3 cans to the surface areas. and create a function. The function depends on the radius. It spits out the surface area. And if I could figure out on that function where the lowest point is, at which radius that occurs, that would tell me how I need to build my can. That makes sense? But do you see all it is finding the bottom of this function, that lowest point? So we spend the first few sections learning how to find lowest points, and at the very end what we do is we come up with word problems that we convert to functions, and then we go find the lowest points. Understand? It turns out though, for a can, if you had a perfect can, I'm kind of going to spoil the surprise here for this problem, but if you have a can that if you make the diameter, we'll call it D, equal to the height, if the diameter of a can and the height are the same, that's the least surface area you're ever going to get. If you build a can any other way, you're wasting material. But, who has a can? Nobody has a can in here. Do you have a can? No. Okay, so we know that there's cans that you buy out of the soda machine are not perfect cylinders, right? They've got the tab that you pull, right? So that's aluminum, and then they've got these weird little grooves. And what about on the bottom of a can? It's indented, right? It like goes up and in. What's that for?
Pressure.
If you leave it in the freezer or you leave it in a hot car, pressure builds up. That little bulb that's pushed up will actually pop out instead of blowing up, right? That's what it's for. So the dimensions of the cans that we have in reality are not a perfect cylinder like this is. And so our function here would change if we're developing a real can. But that's what you would do in the real world. You would have the actual thing you're trying to build, and it would somehow, you would have to modify the function. But we're going to do something very basic here, just a basic cylinder.
Wouldn't
Yes.
they also have to take into consideration like the stretching of the metal?
There's a lot of things that would play into it. You know, are the walls of the can the same thickness as the top and bottom? And then there's aesthetics. I mean, you know, you have the Monster energy drinks, right? That, you know, we want a big can, it's a Monster, whatever, you know, they want to look, you're not going to have this little Red Bull can, right, for Monster, right? I mean, you know what I'm saying? There's a lot to it that goes into it also, right? And so they're willing to pay more for the can if it's going to portray it the way they want. So there's a lot of things that come into play here. Plastic's a totally different thing. Manufacturing process. Maybe it's easier to make a can a certain shape. But we have to start very basic, right? This is where we begin. And then you move into an actual field, you know, whatever your field is, and you go work for a company and you've got a specific problem you have to work on. But it's all about problem solving. Are you a problem solver or not? That's what we're here for. Try and create problem solvers. All right. What? You know? Why are you laughing?
I really hate word problems.
Well, that's something that comes with time, because I didn't like them either. All right, but
Were you always good at math?
no, I was not.
Were you ever at a point where you hated math?
I hated math for a long time. I've loved more math. I've loved math more now, time-wise, than I've hated it. But I think I hated it all the way through sophomore year in high school, maybe junior year. No, probably all through high school I didn't like it.
What made you think?
All right, do y'all really want to know the story? Y'all want to know the story? I'll tell you the story. It can be a lesson. All right, so I hated math because I was in a private school in grade school. And in private schools, there's no like, they don't give a damn. If you don't know it, they're going to put you in the low group, and you're going to be like in the low group, right? So I was like in the C group. A group was all the smart kids, B group was all the like middle kids, and C group was all the rest of us, right? So we were just in there, C group. I was always C group, reading, everything, C group, right? So I didn't care, and I got through, but it was still, our education was still better than what I would have gotten in public school. And maybe I should mute this. I better mute it. I may just say I'm so sorry. I hate talking about myself. It's such a bad thing, but I do think that that can sometimes motivate people. Like if you really are, if you're that student that was me, like you kind of maybe now know, I know who you are. You know what I'm saying? Like you can do it. You got to get up and do it. All right. So we have this section 4.1 that has a bunch of definitions. All right, a bunch of definitions. And I didn't ask you to watch this video before class, so I'm not expecting you to know all these, but I want you to go back and read through these on your own. Watch the video that goes with this, the course video. The reason I'm not going to start explaining every single one of these is because this is a very geometric section. It's very visual, and most people can get things when it's visual. So I'm going to just start with the picture. And what we have here is a continuous function. I can draw without picking up my pencil. It's on a closed interval. So what that means is that it looks like, I don't know, this looks like around -7 is where it starts, goes down, goes up, goes down, and then it stops here. It looks like at 9. So we could say that this function is defined on that closed interval from -7 to 9. That look familiar? This closed bracket means include the endpoints. Okay, so this is the domain of that function. That's the domain. Yes?
Is there any reason for that bracket?
Yes, because we actually have a point. At 9, we have a point, right? If this had been an open circle here like that, then we would have left this as a parenthesis.
No, but like the way you drew it.
Oh, that was a real shitty bracket? Oh, no. Thank you for pointing out that that's a shitty bracket. Is that better?
It's a little better.
I drew the brackets like that, and I was like, what does that mean? Like, yeah.
Is that better?
You curved it, I was like,
Yeah, I didn't mean to curve it. I'm sorry about that. All right, so that's our domain, right? We have a continuous function on a closed interval. And what we're interested in talking about here are first what are called the local extreme values or local maximums. When you hear the word local, you think like San Antonio, right? Something like that. Local compared to like global, which would mean like you're looking at the whole world. So if we talk about local extreme values, what we're saying is if you look at this function, what is the highest point locally? So is it obvious that this point right here looks like the highest point? Maybe on the entire graph, right? But you could also say locally, like this little hilltop right here, that's the king of the hill. So that would be considered a local extreme value, or what we call a local maximum, but it's also the global, or what we call absolute maximum, because it's the highest point on the entire function. Look at this point right here. This right here is the lowest point locally. It's not the lowest point on the whole graph, right? Lowest point on the whole graph's down here. But locally, this is the lowest point. In this little neighborhood, this little area, this locality, this is the lowest point. Got it? Local minimum, local maximum. We have another local minimum right in here. I'm putting those little parentheses just to say, to focus your attention in this little area, right? Local minimum, local maximum, local minimum. Now globally, we said this would be the global maximum, and this would be the global minimum. You can also say absolute maximum and absolute minimum. You'll see it in books different ways. This make sense? What about the endpoints? I think most people would say that the endpoints would look like a local, because you could say like this right here looks like locally it's the highest point. Like if you just look near it, like this stuff over to the left of it, it would be locally the highest. The problem is this: to define a local maximum or minimum, you have to have a neighborhood on both sides. You have to have a region on both sides. So when we look at endpoints will never be local maximums or minimums, ever. They can be global though. I'm going to show you more examples, all right?
So in order for it to be global, it also has to be local.
Yes. If you're, well, no, that's not true. You just said, in order for it to be global, it has to be local. No, because you can have an endpoint be a global maximum, but an endpoint can never be a local maximum. I know it's weird, but that's the definition of local and global. So if you, we can label these, okay? So here are local extreme values. Local maximum here. Now, when we say it's a local maximum, what we're most interested in is the actual value of the function. That's 856. That's telling you how high up that point is. 856 is locally the highest point. This right here, negative 1519. That's how high it is. So it's below the x-axis. Locally, that's the lowest point. And then over here, locally, this is the lowest point. It's negative 4,975. Got it? Now, I can also superimpose on here the global extremes, which would be just this point and this point, right? We good? I'm going to move to a different example. Again, a continuous function, right, on a closed interval. Continuous function on a closed interval. Let's talk about, you want to do global or locals first? It doesn't matter which ones you do. You want to do global? Those are usually the easiest to find. So where's our global maximum? Right endpoint, right? That is our highest point on the entire graph. Agreed? What is the global minimum?
Last hump on the left.
This hump on the left, this lowest point right there. Y'all see it? So if I label these, here we have a global maximum. The value of the function there is 3,800. That's how high up it is. This is our global minimum, lowest point, negative 4,975 again. How about the locals?
At the middle, and then the right one.
So where am I going to have locals?
The middle.
Right here? I'm going to have one here. That's going to be a local maximum. Local minimum. Local minimum. So I should have two local minimums, one local maximum. See, so this is what you're saying. If you're a global max, you have to be a local. See how this one is not a local? See that? Now, these are supposed to have arrows on them. Is this a continuous function on a closed interval? No. It's continuous, right? But it's not closed. The arrows mean it goes up forever in that direction, up forever in that direction. So let's start with the globals, because you said you like the globals. Do we have a global maximum? No. Now, you might be tempted to say infinity, because it goes up forever. But with global maximums, we're looking for a value. And if the function never has a highest value, because that goes up and that goes up, if it doesn't have a highest value, then it has no global maximum. We just say no global maximum. Okay? How about a global minimum?
Yeah.
Yes. Right here. Global. You can only have one. Global minimum would be this one. So if I put the global information in here, we have no global maximum. We have a global minimum right there. How about locals? Two local minimums, one local maximum.